let's add a sine function to a cosine function. So we have a sine function in red here, and you can see that the amplitude of this is 1. And we have the cosine function, which is in black, and again the amplitude is 1. So let's see what happens when we add both of them together. So we get this third function in blue. Now all we've done is add the sine height here with the cosine, and we've got this final height here. So let's have a look at this new function. We'll get rid of the sine and the cosine function just to declutter. Now we can see this new function is another sinusoidal function, but we can see that the phase has changed. So I'll show you what I mean by that. If we were to notice that the y-axis sits at 0 here, if I was to move this y-axis along, say to this point here, then if we were starting at this point here, we would just have another cosine function. So this new function just looks like a cosine function, but the amplitude is a little bit bigger. So that would mean that we could write a new function out, which would just be a cosine function. The amplitude would be different, and there would be a phase difference as well. But there's another way of looking at it as well. We could delay it the other way. So we could move the axis to, say, this point here, and this new function would look like a sine function. And again, the amplitude would be different, and the delay would be different. So we can represent the summation of two sinusoidal functions, that's a sine function, a cosine function, as just one sinusoidal function, or with a new amplitude and a phase associated with it. So let's change these values a and b, and we'll see how this function actually changes. There we can see there. So I'll just let this run, and you can see that the different functions that are going to be generated whenever we adjust the amplitudes a and b of our original sine and cosine functions. So let's go ahead and we'll take this and we'll write it all down mathematically. So what we just seen in the graphical calculator says that if we have a cosine function of some amplitude a, so you've got a cos x, and you're adding on a sine function of amplitude b, so that's b sine x, well that's the same as having a cosine function with some other amplitude k, and it's going to be delayed. That is, there's going to be a phase change by a value of alpha. Now the question is, we have to find the value of k and alpha. We're not going to go through the proof of this, but we can find the value of k by simply finding a squared plus b squared and taking the square root of it. And we can find that angle alpha is going to be the inverse tan of the b upon a. So it's best to work through an example and things will become clear, and at the end of the example we'll put the value back into the graphical calculator and see whether it works. So if we have 4 cos x plus 3 sin x, then we want to write that in the form k cos x minus alpha, and that's x is greater than 0 and less than 360 degrees. So we need to find these values of k and alpha. So we can replace the k cos x minus alpha by our double angle formula. So the cos of x minus alpha is the same as cos of x cos of alpha plus sin of x sin of alpha. Now if we decided to change this into the form of k sin x minus alpha, then we would have just used the sine version of this double angle formula. So that's going to give us our value of k cos alpha cos x plus k sin alpha sin x. So here's the little awkward bit that people sometimes get confused at. We want to equate coefficients. So we can see here that we've got cos x. So the coefficient of cos x here is 4. So this k cos alpha must equal 4. We've written this down here, k cos alpha equals 4. And the same thing goes here. The coefficient of sine x up here is 3. So this k sine alpha must equal 3. And we've written this here, k sine alpha equals 3. So take your time and read over that again if you're not too sure. So now we can find the value of k. It's going to be a squared plus b squared root. So it's going to be 4 squared plus 3 squared root, which is a value of 5. So we want to find the value of our angle alpha. So we know that our tan alpha is equal to b upon a. So we just put in our values for our b and our values for our a. So tan alpha equals 3 upon 4. Now there's one thing to note here as well, is that we're interested in what quadrant it's going to be in. So in this instance here we can see that the cosine here is a positive value. So cosine is positive in this quadrant and in this quadrant. And we can see here that the sine is also a positive value. So the sine is positive in this quadrant and in this quadrant. So when the two match up, that is in the first quadrant, it is positive in the sine and cosine are both positive in the first quadrant, therefore it exists in this quadrant here. So we can say that tan alpha equals 3 upon 4. So the inverse tan of this 3 upon 4 is equal to 36.9, and that is in the first quadrant here. So finally we can say that the 4 cos x plus 3 sin x is equal to 5 cos x minus 36.9 degrees. So let's take this function and we'll put it in the graphical calculator and see whether it does actually work. So let's start off with our sine function in red and our cosine function in black. But our cosine function is actually going to be 4 times the cosine function, so we'll change this to value to 4. So that's going to be our 4 cos x. And we're going to be adding on a value of 3 sin x. So this is our 3 sin x. So those are the two functions we're going to add together to get a third function. So whenever we add those together, we're going to get this function here. So that's the function in blue. So let's get rid of our original sine and cosine just to declutter the image. So we've got a new function in blue. Now that new function should be the same as 5 cos x minus 36.9 degrees. Well, that's the function written here, so this is a 5 cos x minus, now I've changed the 36.9 degrees into radians because we're going to have a radian measure along this axis. So if the theory is correct, whenever I click on this, this graph here should sit directly on top of this one here. And you can see it does, it's exactly the same. So we're able to say then that 5 cos x minus 36.9 degrees is the same as 4 cos x plus 3 sin x. So you might be wondering what the point of all of this is. Well, it's very useful to be able to add and subtract the sines and cosines. It helps us generate waves. Now if we were to go on to more advanced mathematics, which we will do in the next course, we can derive the wave equation, and that wave equation is a bit more complicated than what we have here, and we could do it in, say, 3 dimensions. So there'll be a lot more involved in that than what we've got here, but this is a good start to understanding a part of mathematics and, more importantly, physics, which is involved in waves. So thank you for listening. I'll get you in the next video. Goodbye.